set up? Yeah, go. Okay. So we're Design Team 5. We're working on a load metering and transmission project for ArcelorMittal. I'll quickly go over introductions of our team. I'm Ken.
Chip.
Jay.
Alex.
Matt.
Pat.
Okay.
You're the only one on screen.
Right now? Okay.
On the screen just a little bit.
So in this presentation, we're going to go over background of our project and what our design problem is. We're going to go over the design specifications and requirements of our design solution. Then we're going to go over our various conceptual designs to solve our problem. And we're going to look at a risk analysis of our different problems and go over budget of our chosen solution. So our project background, our company is ArcelorMittal, which is the largest steel company in the world. They have a facility in Burns Harbor, Indiana, in which they cover all aspects of the steelmaking operation, from processing iron ore to making large plate steel. At this facility is it's extremely large. It's probably a square mile, just a guess if I would look at a map, but it's encompassed by many buildings, many individual buildings, which cover different parts of the steelmaking operation, surrounding a central control room. In this entire facility, there can be a peak power usage of approximately 100 megawatts at any time. The ArcelorMittal has the ability to generate about 2/3 of the peak power, but they also have to buy about 1/3 of that peak power from a utility. So they have a generating station in their facility, and they also have to buy part of it from a utility. So because the economics in buying power from a utility and generating power themselves, it's very crucial that at any time they understand what the load is, the total electrical power load throughout their entire facility. So, and it's due to cost reasons, because they're buying power from a utility. They need to know how much they need to generate, and the utility, based on how much they buy, and if they reach a certain threshold, will charge a significant amount more money. So, go to the next slide. So, to calculate the amount of load throughout the total facility, you need to know what the load is at each individual building in their facility. And different buildings cover different parts of the steelmaking process, like cold rolling, hot mill, coke plant. So in order to take all those signals and sum them together, they need to have a transmission network which transmits from load metering devices at each individual building on the different large pieces of large machinery and switchgear, and transmit to the central control room where the signals are summed together, and then the operator in the control room can know what the total power usage is at any time. So they have a current system of doing this, but it's very old. So the system which they have to transmit signals from each individual plant to the central control room was a system that was put into place when they first made the facility in 1964. So these are around 50 years old, and because of the critical nature of the information which is transmitted to generating power and buying power from a utility and the economics of it, they want to make sure that they have a backup solution in place just in case their 50-year-old solution fails. They're really worried about what the lifespan of this system is going to be, although it has been working for the past 50 years. So our design problem is to I guess, remake a redundant solution which will transmit a signal from a plant to the central control room, which could be located up to a mile away. So I'm going to go over their current way of transmitting signals right now. So at each individual plant, they have power meters that are on switchgear and large pieces of machinery. The power meter has a value which ranges from a 0 to a peak value, and that goes into a load transducer, which converts that to a linear variation of a 0 to 1 milliamp current. That 0 to 1 milliamp current then goes through a resistor, which is proportionally sized to the peak value of that individual power meter. So if the power meter which goes to this transducer has a peak value of 5 megawatts, and this one has a peak value of 2.5 megawatts, then this resistor is going to be twice as big as this resistor, so you can get a larger potential difference, which represents the peak value of the power meter. So if you add up all these resistors that are in series, you're going to get a potential difference between this node and ground, and this potential difference varies for the hot mill between 0 to 100 millivolts, and that signal is an analog variation which linearly represents the power variation from 0 to a peak value in the hot mill, which then goes to a frequency modulating device. The frequency modulating device modulates that analog signal with a 1020 Hz carrier. That signal then goes to a twisted pair transmission wire, which can be anywhere from, I guess I should say, up to a mile away from the central control room. And then in the central control room, that signal is demodulated, converted to a 1 to 5 volt signal, that's linearly varying signal, which goes to a PLC. And the PLC can then read that signal and convert it back to a power usage, which then goes into the ArcelorMittal server system, and the operator in the control room can sum together all of the individual building usage, power usages, to get an idea of the total power usage in the facility. So that's our design problem. Now I'm going to hand it off to Nan, who's going to talk about some of our solutions.
Hi, I'm Nan. I will go over our conceptual designs. The first design is the first design is a wireless transmission. Basically, we use a radio transmitter and a receiver to transmit the signal through 1 mile range distance. And the example is FM transmission and FHSS transmission. The basic difference is they use a different frequency band, and because we're supposed to transmit the signal through 1 mile range, so for this design we don't need to buy the 1 mile cable, which will save us the budget. And we have found on the market there has already the actual product for the radio transmitter and receiver, which we can just buy it. However, our system needs to be run 24 hours and 7 days a week, so the reliability is very important. But for the wireless design, it's less reliability and secure. The signal can be easily affected by the bad weather or the other interference, and it may break the connection, and the signal can be captured by the other people or other company. So, and the 1 mile range, we need a large antenna for the transmission. So it will cost a large amount of money and time to build. The second design is the wire design, which is Internet I/O. Basically, it will convert the analog signal to a digital signal and transmit through the Internet cable with an extremely fast speed. For example, for this kind of Internet I/O is Adam 6000. The communication speed is around 10 to 100 megabytes per second, and it actually has 8 analog input and 2 digital output. For each channel, it can be configured by the software, and it's also empowered by the peer-to-peer technology. So we can configure the IP address, use computer, and it will connect each other. And here is how it works. The analog signal goes into the Internet I/O, and it will convert to a digital signal through the Internet cable or the other cable. It can be transmitted through to the receiver side. On the receiver side, we can configure the output. We can configure the output to the 1 to 5 volts and 4 to 20 milliamps, and send to the PLC, and we will get our result. The Internet I/O is much more reliable and stable and secure than the wireless design. The power plant, we have got that the power plant already has the Internet cable already, so we can just plug it and test it. And Yeah, and also we have some concern about this design. The actual product on the market is about $500 to the about $1,000, and it's extremely expensive. And however, the existing Ethernet cable is about 50 years old also, so it may affect our result. So we are concerned about the reliability. Maybe we can get a new cable for the transmission. So we decided the Ethernet cable should be our secondary design. And I will pass to Alex for the proposed design.
So now I've talked about some alternative design solutions. Our proposed design solution is pulse width modulation. I'm going to go over some modulation basics first. Modulation encodes a low frequency signal and a high frequency signal. And the low frequency signal is known as the modulating signal. The high frequency signal is known as the carrier signal. So in modulation, the carrier signal is, the properties of the carrier signal are changed slightly by the modulating signal to encode the signal, and then you can send it over a transmission line. Here's an example of an amplitude modulated signal. So we chose pulse width modulation because it has a very low cost, and we can get all the parts that we need for the most part from the ECE shop. It's also a very reliable solution because we understand how it works, and so we can debug it and fix things if we have a problem. So pulse width modulation works kind of like a digital signal, except it's still an analog signal. The modulating and carrier frequency are compared, and when the modulating signal's voltage is greater than the carrier signal's voltage, then you get a logical 0. And then when the modulating signal's voltage is less than the carrier signal's voltage, you get a logical 1. So this is a PSpice simulation. You can see the modulating signal and the carrier signal, which is a sawtooth waveform. And you get a pulse signal out with varying pulse widths. The next part is the signal transmission. Once the pulse type waveform is created, you transmit it over the mile-long transmission line, which acts as a low-pass filter. This can cause distortion because the square wave is theoretically made up of an infinite number of sine waves. And so if the corner frequency of the transmission line is too low, then our signal will become distorted, and we won't get, it'll lead to a lot of attenuation of the signal. So we plan to use a very low frequency transmission. We're talking about 1 kilohertz as a good transmission frequency. Once the signal is received, then it's decoded by a low-pass filter, which should give us a clean sine wave representing the power usage of the mill from 0 to 100 megawatts. The power level of the mill shouldn't change more than 1 hertz, so we can keep our corner frequency pretty low and still get a good reading on our output. I'm going to pass it off to Pat now, who's going to talk about the application.
Hello, I'm Patrick, and I'm going to talk about how we're going to actually employ pulse width modulation. As we already mentioned, the specifications given to us by our sponsor was to take an input from the transducers in a range of about 0 to 100 millivolts, and then to make a ratiometric output in the range of about 1 to 5 volts and 4 to 20 milliamps. So I'm going to break down my discussion and talk about the transmitter, the channel, and the receiver. So for the transmitter, as we already mentioned, the most common way to do it is to use comparator method. It's very subjective on which one you might think is easier. You can either use a microcontroller, which you put an analog, the modulated signal in, and the rate at which the pulse changes is done by coding. Or you could use a comparator and you'd have to generate your own oscillator or sawtooth or triangle wave generator and have it input into your inverting terminal and reference to the modulated signal to get your pulse width output. Another way to do a transmitter is actually to use a monostable multivibrator such as the 555 timer. This one relies on the rising or falling edges of to be triggered. You have your modulated input coming into the port, and then you trigger like a pulse train to capture the rising and falling edges. Here's another one, which transistors will alternate. When T1 is on, T2 will be off, and again rely on the rising edge or falling edge of the trigger. We've already talked to our sponsor, and according to the electricians, they have a lot of twisted pair wire available for transmission from the transducers. There are risks in using it, such as if it is subject to attenuation at high data rates. But essentially, if you're using twisted pair, it's going to eliminate crosstalk between the channels. One is wired to our output from the transmitter, and the other would be wired through ground. The ground should not be tied together from the receiver and the transmitter to get any common mode noise. But essentially, as what Alex mentioned, we got to be sensitive to the signal processing fundamentals we learned in 366. This is a convolution issue. Our pulse is being made up of several different sine waves, and what we don't want is for our pulse to end up looking like this. So we are going to we're going to observe the Nyquist rate, and also we need to learn from the lessons learned from the telephone company, and they recognize the bandwidth of twisted pair, and what they observe as their bandwidth is about 4 kilohertz. So we want to be in that range about 1 kilohertz to 4 kilohertz, and not get all the way up to the megahertz range and have some significant distortion. So at the receiver, as Alex mentioned, it is really as simple as doing a low-pass filter, which is going to take the average of the duty cycle. So here's some simple examples of some low-pass filters. Trouble with these is that you will still get some oscillation at the output. So in order to minimize those oscillations, you need to go higher in orders. Some problems with using inductors is that you are going to cause a little bit of interference with other surrounding components as well. Inductors tend to be noisy. So in our proposed receiver, we are going to use an active low-pass filter of a higher order, and we simulated a 5th order low-pass Butterworth filter, and there was literally no distortion at all. So our proposed design, as Alex said, that we can get most of our parts in ECE shop. We're going to go with just the comparator method and generate our own sawtooth generator. We're going to transmit over a shielded twisted, hopefully a shielded twisted pair wire. That would be ideal, but even if we do use the unshielded, we don't anticipate any attenuation. And then, as I said, we're going to build a 5th order low-pass Butterworth filter and send it to the PLC. And then I'm going to pass it on to Cheng, who's going to talk about risk analysis, budget, and management.
Hi everyone, my name is Chen, and I will go over risk analysis, budget, and project management. For risk analysis, the 3 major risks we have is attenuation, fabrication error, power consumption, and heat. For attenuation, since we are sending the signal as long as 4,000 to 5,000 feet, we do have attenuation problem. Even though we design pulse width modulation and keep the frequency as low as we can, but we still gonna have some attenuation problem. And to make it even worse, the twin twist cable that we are given by the sponsor has been set up for 50 years. They don't even have very good knowledge on that cable, so that's our concern. Fabrication error, we have resistor, capacitor, and inductor tolerance, and we have soldering error maybe. And those may not be big arrows, but we do concern that, because even if a very small arrow could cause a very big problem for us, in the worst case, it could fail our final product. And power consumption and heat. The entire system shouldn't cost like 1 watt of power. But since it's running 24 hours a day, 7 days a week, and we cannot set a break to it. So the heat generator may be a problem at some point. So that's our concern. And budget, since we are building it from prototype, and we will be using a lot of electronic components which can be taken from VC Shop for free, and chips like op-amps and other 555 timer maybe, those can be taken from VC Shop for free as well. We do need PCB fabrication because we want hand a fabricated printed circuit board to the sponsor. We give an approximation of $100 for PCB fabrication. And since the device will be mounted into a environment, which is an industrial environment, we want to casing it, and so that we can prevent outside source of interference. And we give an approximation of the case to be $30. And mounting devices, we need some mounting devices like mounting rail and etc. And we give an approximation of $50, and that gives a total of $180. And the rest of the budget will be used to add some flexibility, and we may have some failure at some time. We can probably have some adjustment on design, so we have more budget. And project management. The project will be divided into 5 stages, and we have finished the first stage, which is design and simulation, and we are moving on to the next one, which we will be building prototype. And hopefully we will finish building and testing the prototype by middle of October. And we will have the fabricated PCB according to the plan in the beginning of November. That will give us like a month to do the final testing and problem resolving. And team, we have 5 members on the team: Alex, Patrick, Nan, Ken, and I. And Alex, who's the document prep, and he's also responsible for designing the pulse width modulator. And Patrick, who's the lab coordinator, and he will be designing pulse width demodulator. And Nan, who is the webmaster, and he will design a simulation of the transmission line so we can use it in testing. And Ken, who's the presentation prep, and he will design a simulation of the transducer, which can output a power signal so we can use it to test our system. And I'm the manager, and I will also be responsible for testing and mounting. And all of us will participate in the project, like building the circuit and fabrication. So it's just like Alex will leading the design of pulse width modulation. And conclusion, we went through background in which our project is to send a low signal from transducer located in a substation to the PCB, the PLC. The PLC located in the central dispatch. And the design specification and restriction, we need to take the input of a 0 to 100 millivolt low signal and send it 1 mile and output a 1 to 5 volt PLC signal. We do have some restriction. We will build our system parallel to the current system, and we cannot shut the current system down, not even a minute. And we came up with 3 conceptual designs: pulse width modulation, wireless, Ethernet I/O. And even though wireless and Ethernet I/O are very good ideas, and we think they will work, but they are pretty expensive and they went over budget. So we decided to go with pulse width modulation, which is cheap and feasible, and we can actually design it and build it and test it, and it's reliable and no budget. since pulse width modulation is fairly inexpensive, we will be able to control the budget within about $200. So that's our presentation. Thank you for listening. Any question?
Well, I guess. So if nobody else has a question, I guess I have a question. So the amplitude is the most important thing in the signal you're transmitting, right? If the frequency changes, that doesn't really matter. All you care about is the amplitude, which represents the power usage. Is that correct?
The frequency of the signal shouldn't
No,
change.
the duty cycle is what we're
Yeah,
concerned
yeah,
with,
yeah,
pulse
the-
width modulation.
It's the pulse width, it's not the
Right,
frequency.
right. But I'm saying the initial signal you're given, you're looking at the amplitude
Yes,
to
the
determine.
initial signal we're given is a 0 to 100 volt, a millivolt analog signal.
Okay.
And what we need to do is take that 0 to 100 millivolt analog signal and figure out how we're going to transmit that information from that signal to the control room and provide a 1 to 5 millivolt or 1 to 5 volt signal to a PLC.
Right. Okay. All right. Thanks.